it's like the sine, you know, it's poorly behaved, sure, but its overall oscillation is never more than 1. So if you kill it with an x, in any neighborhood of 0, it's going to be arbitrarily small. Oh no, certainly. Just at 0, at 0. So here's a function. If you ever have to come up with one that's continuous at a single point and then goes to hell everywhere else. Now, usually we're used to seeing them continuous on an interval and just bad at 1 or 2 points. Here's one that is very poorly behaved everywhere except at the origin, where it seems to be.
I'm taking notes from the mouse, but goes to hell on every place.
Oh, she's very religious. No.
So you can make one building a library with just about any one or something by multiplying by x minus x.
Yeah, you can move this whole thing over. Yeah. That'd be a good problem. Amanda would like that. Define a function on the interval 0, 1 that is continuous at 1/2 and discontinuous at 1/2. I don't know how to do that.
Amanda, you're very good.
But you see how to do it? You just shift this whole thing to the right by subtracting something. It would be the Dirichlet function, x minus 1/2 here, right? You use
x minus 1/2.
X minus 1/2 times, right, x minus 1/2 times delta of x. That would pull the thing down at 0. Or at 1/2. At 1/2, make it continuous. Is the Tomei function is well, we can define it on the whole real axis, but we'll just integrate it from 0 to 1. Let's see if we have the negotiable. It is 0 if x is not rational, and it is 1 over q if x is equal to e over q. P and q in lowest terms, p and q are integers. Q is not 0. So, and every irrational is 0. And like, if x is 1/2, the function is 1/2, right? At 3/2, it's 1/2. At 5/3, it's 1/3. At 1, it's 1. So it's like a bunch of stalactites sticking up various heights along the real axis. At every rational, you get the rational in lowest terms throughout the numerator, look at the denominator, let it go up 1 over that denominator at that rational. So it's sticking up.
What's that second last name?
Second to last?
Yeah.
P and Q are both members of the integers. They're both integers.
Oh.
Q is at 0, or this wouldn't make sense. And they both have, I guess,
Which common multiple?
yeah, actually the GCD, but the highest common factor, greatest common divisor of P and Q is 1. So you reduce it to the lowest terms. Then you look at the denominator and map that from 1 over the denominator. So the function's never bigger than 1. But it jumps around a lot. Here's a problem for Tuesday. Who would like to show this? The Tomei function is continuous almost everywhere. Almost. Yeah. You want to try that one? Sure. You got the weekend to blow it. Here's a hint. It's continuous on the irrationals. And once it's continuous on the irrationals, you capture the irrationals you know, the first rational epsilon, second epsilon squared, like we did the other day. And show that, well, you know that the measure, the ordinary vague measure of the rationals is 0. So that's a set of measures here. So if it's continuous on the complementary set, namely the irrationals, you're done. Here's the great observation of the key to it. I'll save you a few hours. If you have an irrational number, remember the rationals are dense. So there's always, in every little interval, there's always more rationals. So the danger is that, geez, there's a rational arbitrarily close to the irrational at which I'm trying to show continuity. But you can control how big the denominators are. So you can always get, given an epsilon, you can always get 1 over q under epsilon. Well, how do you do that? Well, first, given epsilon, you find a 1 over n that's less than epsilon. And then you strike in an open set containing your point all of the multiples of a half, a third, a fourth, a fifth, 6th, 7th, right? Up to and including capital N, right? So that's a finite number of multiples of these things. They are the dyadic fraction. Right? If you get rid of all of those things in the middle, right? Now, since it's a finite set that you've taken away, you can get inside that. You can still get on either side of your point that you want to show continuity and push all those other fractions out. So the only rationals close to you are ones that have really damn big denominators. Namely, 1 over that denominator less than the given epsilon. See how it works? Yeah, think that through. All right, is the Tomei function continuous? Or is it integral? Well, you know it's Riemann integral. By Lebesgue's theorem, function that's bounded and continuous almost everywhere is Riemann integral. Well, this is what this is. Is it Cauchy integral? Well, okay. So, yes, sir.
Isn't the Riemann integral have the same fundamental theorem?
Yeah.
So like what I'm trying to say, like, how would you take an integral, like there's an integral, like on irrationals, like 2 squared or 2 squared 3?
It's a set of measures 0. You extend Riemann integrability by stopping and starting. You know, I will surround the first rational by epsilon to the first, the second rational by epsilon squared. So I've got all the rationals laid out there where the thing is poorly behaved, and I've surrounded them all by powers of epsilon. Geometric series is total length is going to be epsilon over 1 minus epsilon. Okay. And now what I do is start and stop my Riemann integral between those. Get the value of 0, right? And then I let epsilon go to 0. So that's it. These arguments are very subtle. So let's see. Let's look at 2.4 for next time. And let's see if I can do 2.5. Dave was going to do this, but let me see if I can do it.
I really had absolutely
I
no
don't
time
know.
for
He wanted to eat lunch. It's okay.
But not just that. Like after I had lunch, I tried to sit down and do something. I did for about